Hi, this is Dane Quinn from the University of Akron, and this is a series of video lectures for engineering mechanics. And today, I'd like to talk about equivalent systems and correspondingly equivalent parameters for those systems. We're going to deal with a couple of examples, three actually, that we have seen before in previous lectures. And so I want to really look at those different examples and the resulting equations of motion here and show how they are, in some sense, equivalent. So here's the basic system that we always start off with, a spring mass damper system. We have a spring of stiffness K, damper, coefficient B, and mass M. And this block is constrained to move horizontally. So we'll measure the displacement with x. And the resulting equation of motion is given here, mx double dot plus bx dot plus kx equals 0. And this is, of course, our spring mass damper system. And we derived the equations of motion for this in a previous lecture. So in that lecture, one of the things that we saw is the response parameters. So we can identify those response parameters as the natural frequency and damping ratio. And in terms of the system parameters, namely m and b and k, we find that the natural frequency is the square root of k over m. And the damping ratio is b divided by 2 square root of km. We saw these in previous lectures as well. A lot of this, what we're doing right now, is going to build on the stuff that we've done before. So when we talked about how to solve the equation of motion, right, we essentially identified the natural frequency and damping ratio as important response parameters. Likewise, we had the decay rate sigma as zeta omega n. This is essentially the exponential decay rate of the free response for this system. And we identified the damped natural frequency as omega n times the square root of 1 minus zeta squared. For an underdamped system, where zeta is between 0 and 1, then this damped natural frequency represents the frequency of oscillation as the system decays. The important takeaway from this lecture is that any linear constant coefficient, and constant coefficient here implies that the damping coefficient B and the stiffness K are constant. So any linear constant coefficient, single degree of freedom system. So there's only a single coordinate that's needed to specify the configuration. So any system that fits this general framework can be written in this form, like mx double dot plus bx dot plus kx equals 0. And that'll give rise to what we will refer to as equivalent parameters or equivalent systems. So here's another example that we derived previously, right? So now we have this block and it's on an inclined plane. And it has actually a damper B, but two springs now, one on the left, K1, one on the right, K2. Again, previous lecture, we went through and we derived the equation of motion as measured from the static equilibrium position as mz double dot plus b times z dot plus, well, now it's K1 plus K2 times z equals 0. So if you remember maybe a previous class, you might have said that, oh, well, we can replace this combination of springs, K1 and K2, by a single equivalent spring of magnitude or stiffness, K1 plus K2. And that's really what we see here. If I think about K1 plus K2, this is like an equivalent spring. So when we derive this, we actually didn't do that. We just derived the equations of motion using linear momentum balance. But what we found out was when we wrote the equations of motion, they ended up looking like this, right? So the K1 and the K2 added together and sort of appeared naturally in that combination. So now we can look at this equation and then look at this equation and see that they're really similar. The only difference, in fact, is that we've replaced the original stiffness K by this equivalent stiffness K equivalent, which was K1 plus K2. So if I want to identify the response parameters, I can do that again, right? Here, omega n is the square root of, well, K equivalent divided by m in this case. And so that's going to be K1 plus K2 divided by m. Essentially, we identify this equivalent stiffness, and then we use the expressions for natural frequency and damping ratio. So the damping ratio becomes B divided by 2 square root, once again, K equivalent, times m. So substituting in the values for this system, this is K1 plus K2 times m. These equivalent system parameters are identified by comparing the equation of motion that we have with our equation of motion for a sort of standard spring mass damper system. And in doing that, we can say that, oh, well, this combination K1 plus K2 plays the role of the original stiffness K in this simple problem. And so that's why we say that any linear single degree of freedom system can be written in this form by identifying the equivalent parameters. So let's look at a little more complicated example. Again, one that we've done previously in one of our earlier lectures. Here we have a disk. It rolls without slip on the ground. There's a spring of stiffness K1 attached to sort of the outer radius of this spring wrapped around. There's an inner hub and a spring of stiffness K2 is wrapped around that inner hub, and then a linear damper is attached to the center. I would refer you to the previous lectures, right, for how to go through and model this and develop the equations of motion. But when we did, we found that the equation of motion took the following form: 3mr squared over 2 times theta double dot plus, this term and then this term, which has both K1 and K2 in it, times theta. So again, comparing to our spring mass damper system, right, this term looks like an equivalent mass. This term looks like an equivalent damper. And finally, this complicated term looks like an equivalent stiffness. So once again, we can identify equivalent values. MEQ is 3mr squared over 2. The equivalent damping here is just BR squared. And the equivalent stiffness of this system is 4K1R squared. And then this last term depends on K2. So once again, by comparing the equation of motion with our equation of motion for a spring mass damper system, right, which I will remind you was just mx double dot plus bx dot plus kx equals 0. Right? So again, that's our sort of standard equation. Then we can identify equivalent parameters. So once again, we can also identify the response parameters. Here, the natural frequency is, again, just K equivalent divided by M equivalent. Obviously, for this problem, a little more complicated, right? 4K1R squared plus K2R squared divided by 4, all divided by 3mr squared over 2. But, okay, we can always calculate this equivalent stiffness, and we can calculate this equivalent mass, and then find the natural frequency. Likewise, the damping ratio is B equivalent divided by 2 square root K equivalent times M equivalent. So, just substituting in here, BR squared is in the numerator, the denominator is 2 times the equivalent stiffness, written here, times the equivalent mass. And if you go back and look at the lecture where we derived this equation of motion, right? These are the results and these are the values of the natural frequency and damping ratio that we identified. So one way of thinking about this is that if I have one of these linear constant coefficient single degree of freedom systems, I can identify an equivalent spring mass damper system. Here, the equivalent mass would be MEQ, right? So in this case, the equivalent mass would actually be whatever number came from 3 times the mass of the disk times r squared divided by 2, right? So I mean, again, this is just a value that we can calculate based on the system. And if I use that for the mass of the block, right, we have the equivalent mass. Likewise, equivalent damping, equivalent stiffness. So once again, if I calculate these equivalent values based on the parameters of this system, and I go through and I decide that I'm going to measure this displacement with a variable theta. Probably wouldn't do that normally, but right, it's just a variable. I can call it anything I want to. Then the equation of motion for this spring mass damper system is precisely the equation of motion that's given here, right? Because all these parameters are the same. I actually use the same variable to measure the rotation of the disk as the displacement of the mass. Again, it's just a name. And again, the resulting equations for these two systems are exactly the same. So again, the response of systems with equivalent parameters, right, they can't be distinguished from one another. If you were to, say, go into the lab and measure the response here, go into the lab and measure the response here, and I just gave you that time trace, you wouldn't be able to tell me which system that response came from. So in that case, we say that the systems are equivalent. So really, we can take any, again, linear constant coefficient single degree of freedom system like we're studying here, and we can write that as an equivalent spring mass damper system. So it's just a useful way of thinking about a lot of the systems that we'll deal with. And this works actually for any linear constant coefficient single degree of freedom system. And it doesn't matter where it comes from, right? Obviously, I've given 2 mechanical examples here. If you're an electrical engineer and you want to go study RCL circuits, those equations are in this form. You can identify an equivalent mass, equivalent damping, equivalent stiffness for an electrical circuit, right? Or some hydraulic circuits, really lots of different kinds of systems, and even things like biological systems, right, could behave like our spring mass damper system. So it's a nice way of thinking about that in a physical context. So that's it, just a quick lecture on these equivalent systems. If you have any questions, as always, please let me know. I'm always eager for feedback, good and bad, and happy to take email, phone calls, you can, whatever. Email is probably the best way of getting in touch with me. But please reach out, let me know what you think, and if there's anything that you have a question on, don't be afraid to ask. Thanks a lot, and I will talk to you again. Bye.